So it's a pleasure to welcome to the Random Interaction Seminar Rituparno Mondal, who is now currently in University of Goettingen and will be moving to University of Chicago soon. I think Rituparno did his PhD with was it Srirama Chandan?
Yeah, it was with Chandan at the end when Chandan retired. Sriram was officially my guide for a year.
Okay, so Sriram and Chandan at IISc, and then he spent some time in, I believe, RRI with Madan, and sorry, NCBS with Madan, sorry, not RRI. And then he moved to University of Goettingen and is now moving to Chicago soon. So he will be telling us about dynamics and rheology of glassy active matter. So over to you, Rituparno.
Thanks, Professor Sen Sharma, for this nice introduction. So, as you mentioned, I'll be talking about my research on glassy active matter. This is also known as active classes. So, here is the outline of my presentation. So, I'll start with my overall research interest. Then I'll explain what is an active class and how to model it and what is its behavior and phase diagram. At the end, I will be discussing some of its rheological behavior. For example, if you take such an active glassy material and do a shear experiment, how it will respond. And I'll end with a summary and outlook. So let's start with my overall research interest. I'm mostly interested in the field of soft matter and non-equilibrium statistical mechanics. And I worked on these key topics like glassy system, athermal or granular system, non-reciprocal systems, application of machine learning in soft matter, active glassy systems, some problems in biophysics, etc. And today I'll be discussing about active glassy system. So let us first try to understand what is the definition of an active glassy material. It's essentially an active material which is due to very high density has glass-like behavior. So in this slide, you can see a picture on your left, which is a picture of an active glass. I mean, it's a picture of a tissue which can be considered as an active glass, and then each cell, which are the constituent of this tissue, can be considered as a representative active matter system. And because of very high density inside tissue, because of very high packing density, it shows glass-like behavior. Now, before I move on to our discussion on active glasses, I also want to briefly mention what I mean by active matter system and what is a glassy system. So active matter is essentially a simplified and idealized version of living matter. It's a system that can use stored or ambient energy to create systematic motion. So you can see two movies here. One is a movie of bacteria moving in a colony. On your right, you see a movie of cell-propelled rod-like objects. This is a granular matter experiment. So when you vibrate the material, this rod, which are asymmetric in nature, starts to propel themselves in the background of beads. So the main feature these systems have is these particles, which are constituting the whole system, are driven at the scale of each particle, and they are driven away from equilibrium by this kind of driving. And this system shows very exotic collective behavior. Here in this slide, I also have shown a few other examples, and I tried to categorize them. On your left, you'll see examples which are more biological in nature, like assembly of bacteria or actomycin assay, which are nothing but collection of cell-propelled rods, but these are more biological systems, which are naturally very complex to understand. And then in the middle, you see relatively simpler system, which is synthetically prepared in soft matter experiments. There are two examples. One is assembly of robots. And in the other example, you see light-activated colloids. So when light shines on them, they start to self-propel, and they form these tiny active clusters. On your extreme right, you see movies from simulation, which are even simplified version of this experiments, where you see two examples. One is assembly of self-propelled rods, and in the lower one, you see assembly of self-propelled spherical particles. and these are known as active Brownian particles. And for most of the talk that I'll be describing systems which are motivated from this kind of. So I'll move on to the next topic, which is
what is an assembly of robots? What's an assembly of robots? Are they self-driven or they're responding to some external field?
Sorry. Yes. So
this assembly of robots in the synthetic system.
So in this particular example, these are simple robots. I mean, in principle, you can create complex interaction between them. And so here they only have spherical interactions, so they don't overlap with each other, but they have. Sorry, there's a background noise.
Yeah, please go ahead now. Yeah, please go ahead.
Yeah. So in this particular example, these robots are just self-propelled and they are confined in a 2D chamber. But in principle, you can also drive them externally with a particular way of, you can implement some programming like how they will move in them. And also you can use complex interaction like leader follower. You can do lots of stuff there. But in this particular example, these are just self-propelled objects confined in a 2D geometry. And this is also confined in a circular arena, so they cannot escape this. Okay, so
yes,
now move for discussion on on glasses. So I'm just having some difficulty in changing the slides. Okay, yes. So now I'll try to answer what is glassy material. This is a difficult question to answer because the idea of glass transition is not very trivial. But for our purposes of the discussion today, we can consider glasses to be just a disordered solid. You can see glassy materials all around us.
Glasses. I always find active matter very hard to understand. Like, same question. You have an external source of energy which is getting converted into. Is this all there is to active matter, or is it a more specialized definition?
Yeah, so I mean, active matters, as I said, it's a simplified version of living matter, and you can imagine they can be of different sorts. So I just tried to give examples where mostly they are self-propelled, but you can have different forms of activity. For example, you can have a assembly of cells where the cells have death and birth. That can fluidize the material. So this is form of activity. You can have size fluctuation. You can have a network where there are motors which are creating local active stresses. So there are different versions of them. So the kind of examples I've chosen are of more or less of a particular category where the particles are self-propelled, because this is what I will be discussing in most of my presentations. So I have chosen actually a subclass of them, but in general, they can be of different sorts.
So theoretically, you're not making a theoretical distinction into any subclass. You're saying, look at the systems which are of this particular kind in nature and we'll call them active matter and have some description for them.
Right. And then I'll take a representative class of them and try to see how the glassy, if they are forced to form a glass, how the glassy behavior in those particular system will behave. And then you can take another class and then ask the same question. And then one can look for universality in all those active classes and all that. So,
I have usual example of, suppose I put voltage across a wire, then on average, the electrons are moving in a particular direction.
Right.
Normally, you would not think of this as active matter. So, this is also external energy getting converted into some directed motion.
Right. Yeah. So,
active
yeah, I will not prefer them to call active matter because so these are externally driven and most of the particles are moving in one direction without any interaction. So whereas in typical active matter system, when we look at them, what we see is that the particles are driven at the scale of individual particles. They have their own choice of direction. Right now, because of some kind of interaction, they might get aligned, but they are not moving in a particular direction because of a global field like gravity or electromagnetic field. Right. So in that way, these systems are different. So here you can think of this active as noise, which in principle can drive them in different direction. I mean, again, as I said, it's possible that they can align because of some complex interaction. So they can, in principle, move collectively in a direction. But it's also possible that they move isotropically in different direction because the active forcing that you're applying, in principle, can be different for each and every particle, right? And
in that case, is there a further classification I have to make between active matter without externally imposed current and active matter with? I mean, are you trying to say that examples like the one Rajdeep gave are not okay because that's just an external current imposed by voltages or whatever, and so it's a non-equilibrium current carrying state?
right.
But you're saying active matter is individual particles get propelled in some direction with some way. But can there be active matter with a current carrying state versus not? I mean, is that also an important distinction?
Yeah, definitely, right? So you can imagine, let's say you have a bunch of bacteria and then there is gravity. So that effective behavior you see is a collection of those driving that each bacteria is having because they are moving by themselves, and also there can be an external field. You can also apply magnetic field to magnetoactive bacteria and have the effect of both a global current that you are creating in the system by applying a field, and also they are driven locally because they can consume energy at the scale of the particles, right? So you can have both of them.
Okay, and so these will correspond to two different terms in some equations you write down.
Yeah, definitely.
Okay.
Right. But for the discussion today, I will not have any term which will create any global current. So the only kind of active forcing that I'll be having is where each particle is driven by a noise. I'll describe them in detail later, but the kind of forcing will be specific to each particle and they are not coupled with each other. Okay. Now, sorry, are there any questions on active matter?
I had one naive one. You defined active matter to be a collection of particles which have an internal energy source. And as far as I could understand, this energy source is not subject to any kind of conservation or something. It's just some flux of energy that you have in some way. And typically, you're also talking about some kind of active swimmers or something. But usually, if you're giving examples of bacteria and all, they usually respond to some kind of a gradient, like in chemotaxis or something. They have some external gradient with which they are moving. I was curious about this fact that usually, I mean, you would have some limit to the energy that a cell can expend as well, right? Is there some time scale that you're looking at in which this sort of, say, a bacteria wants to move from one place to another, but gets tired over time? Is that not a consideration in your models? Or?
I guess if you want to understand in that way of how much speed it can attain, I think the proper formulation will be the stochastic thermodynamic approach, where you consider each bacteria to be a machine, and then how much energy it can consume, what should be the efficiency, etc. Those kind of questions can be addressed. But for simplicity in my approach, what I do is that I'm just considering each particle to be driven with a constant force and the direction changes over time. Okay. And as you mentioned, that there can be, in principle, gradients of, let's say, food or material, and systems can respond to that, right? So in principle, these are all terms that you can add in the equation of motion of these particles. Let's say there is a term which is gradient of some field, and the field can fluctuate, and then you can have two fields, and then fields can be coupled, and then the particle can respond to one field in an attractive way. It can get repelled from the other field. But these are all complexities that in principle you can build up. But what I'll try to show is that even the simplest model that you have, where you don't have this kind of complex terms, in terms of understanding its glassy behavior, it's still kind of complex. At least it was not very difficult to me to understand. If you don't have these terms, even the simple system is quite interesting.
Okay. Thank you.
So Rituparno, just one thing. So can I define these systems as like tiny engines which are interacting with one another as opposed to particles? Because you say something is happening at the single particle level. So these are like tiny engines, right? I mean, those streamers or whatever that you showed.
Yeah,
That means at the level of a single particle, I can talk about, the heat being, fed in and work being
production
something
and
of.
yeah, you can definitely do that. Yeah,
Sorry?
so you can definitely do that. So you can think of entropy production at the scale of particle and efficiency and heat being dissipated
At
like
the single particle level.
at the single particle level, definitely. Yeah, but my approach is to think of them as a material which is forming a glass. So my approach is to think of them as a liquid, some parameter regime, and then try to see when and under what condition they form a glass from the perspective of a collective behavior. So I'm not taking that approach where I'm considering them to be engine and trying to understand its efficiency, etc. But definitely it's an interesting and nice approach. Yeah, and some people look at them in this way to understand its efficiency and reproduction. Like for example, what kind of dynamics you should impose at the scale of the particle to minimize the entropy production and to achieve certain goal, right? In terms of efficiency. So some people do that. Yeah.
Okay, thanks. Thank you.
Okay. So now, if we look around us, we see all this example of glasses. So like, for example, this ceramic containers, metallic glasses, window glasses, wine glass, or even like the Gorilla Glass in our smartphones. And it will not be an exercise all like the modern age as the age of glass, because you see we are surrounded by so many disordered glassy materials. In fact, to celebrate the crucial role of glasses that in society, in science and technology, United Nations has declared 2022 as the International Year of Glass. So let's look at the glass transition scenario more closely. So here you see a movie liquid. This is a polydispersed liquid, and by polydispersed I mean a liquid which is made of particles of different size and different sizes and with different interactions. I chose this particular example because here, because of different sizes, it's not easy to form a crystal. So when you reduce the temperature of such a liquid, you see that they become like a solid, but it lacks translational order. So that's why you see some structure which is disordered in terms of structure, but it's solid. So if you look at the particles, you see they are only just vibrating. If you look at the motion of particles inside such a liquid, at high temperature, they typically do Brownian motion. And if you reduce the temperature, then you see that the particles gets caged within a small compartment created by the neighbors. So it's a temporary caging that you see, and then it uncages and again gets caged another compartment and keeps on doing this. And as you reduce the temperature too close to the glass transition temperature or below, you see that the particles are typically completely caged in the kind of temporary structure that the neighbors create, and it never goes out of those cages, right? For the typical time scale of simulation or experiment. So caging is a very strong signature of glass transition. So when you see caging, you can guess that, okay, maybe the system is going to approach a dynamical arrest. We can make this idea of glass transition more quantitative. Let's look at some data from simulation. So this is a simulation of Covenderson glass at standard glass former. We don't need to know about the glass former in detail because the quality features are similar if you take any other glass former. So this is from a classical simulation of a binary mixture or a glass former. And what you see is, if you look at the mean square displacement, so this is the mean square displacement of individual particles as a function of time. At very long time, at high temperature, they are diffusive. And then as you reduce the temperature, the diffusion constant goes down. So you can extract the diffusion constant from these curves and plot as a function of temperature. And when you plot them as a function of temperature, you see that they go down very rapidly. So the y-axis is in log. So you see that the decrease is quite a lot. And you can also try to see where it goes to 0. So this will be an extrapolated point. And if you extrapolate it, I mean, if it follows the extrapolated behavior, that means below the temperature, the diffusion constant goes to 0 or to very low value. So for all practical purposes, you can consider the material to be a solid because there is no diffusion taking place. And at relatively higher temperature, you see it's a liquid, and this is the response with respect to temperature. And you can see similar behavior if you look at the density autocorrelation. function. So this is a relaxation function. This tells you how the density relaxes. So if I take a uniformly dense solid and I create some density, and then how the density will relax. It relaxes exponentially, and as you reduce the temperature, you see the relaxation becomes slower and slower. And you can extract time scale from each of these graphs and plot as a function of temperature. You see that the time scale increases, right? So it's just the inverse behavior of the diffusion constant, and you can again fit it and extrapolate it to see where it diverges. You get a similar point, and for a simple and practical purpose, we can call that point a glass transition point. So below which the system is glass, that is a disordered solid, above which it's a liquid. Okay.
So how well is this Vogel-Fulcher law respected in real systems?
I mean, there are many glass forming systems which follow this behavior. This is also called a fragile glassy behavior because of the fragility parameter you see here, which tells you that it bends quite rapidly if you plot as a function of 1/t. There are some other material which doesn't behave like this in a way, or I mean, you can think of them as Vogel-Fischer Taman forming material, but the corresponding temperature is 0. And these are known as strong glasses. So most of the glassy material that we see are they have either strong behavior or fragility. So typically the network forming glasses like silica, the window glasses, these are strong glasses. They don't form Vogel-Fischer Taman. But then there are other glasses, colloidal glasses. They form. They follow this.
Second question is, how is this diffusion constant related to shear modulus? Because I would think that it's a liquid if the shear modulus is 0, otherwise it's a solid.
I mean, see, it's not a simple Newtonian liquid, even close to the glass transition, right? So it's a viscoelastic liquid. So you need to have a frequency-dependent definition of that.
Zero frequency, the limit of zero frequency.
I see. Yeah. So then it's a liquid, but the corresponding. So you can think of this material as having both both of this kind of modulus, and then I guess even if you look at the viscous loss modulus, you see that the viscosity is actually going, because the time scale can be related to the viscosity, right? Because if the material is relaxing slowly, you can imagine it's having very high viscosity because it's not being able to flow too much. So the viscosity is going to diverge. So it has a finite viscosity above glass transition point, and below it has a finite viscosity from this predicted behavior. I mean, you might argue that the prediction might not remain the same if you go to lower temperature, but if it follows the same behavior, then below this the viscosity is in glassy material.
Okay.
And here is another. So I told you about caging, which is one very important feature of glassy material. This is another one. This is known as dynamical heterogeneity. Here you see two pictures. One is from an experiment in colloids, and another is from simulation. So in the experiment on colloids, what you see is that each particle is colored according to the displacement it had over a time scale. And what the color represents is the bluish color represents small displacement, and the brown or the reddish color represents large displacement. So naturally, what you can infer is that all the slow particles are kind of clustered in space, and all the fast particles are also clustered in space. So there is a phase separation kind of thing happening between the fast and the slow particles. By this, I don't mean that there are particles which are perpetually fast or perpetually slow. The identity of them also switches over time. Particles which are fast now will become slow the next moment, and the particles which are slow now will become fast. But if you look at the system at any moment of time, for a small interval, you see there are particles which are moving slowly and they segregate in space, and there are particles which are moving fast. They also segregate in space, right? And you see similar behavior here in simulation, where the displacement of each particle is marked by vectors, and the vectors are large in some region, like here or here, and then the vectors are very small, almost like a dot in some region. So the displacements are quite low there. So both of them are showing the signature of dynamical heterogeneity, and this is also a typical behavior.
By your definition of dynamical heterogeneity, would you expect a critical system to show dynamical heterogeneity or no? Just a conventional second order critical point. I don't know, liquid vapor critical point.
I think they show, because you see they show very large correlation length, right? But I can see only differences when we talk about the second order kind of phase transition. You look at the correlation functions in terms of the order parameter, right? So here I'm looking.
No, let's leave all that out. Let me just say I will tag water molecules in the exact same way and do the same image analysis you're doing.
Right. Then close to you are saying that close to the,
and I'm at the critical point.
Right. So I think it will be more uniform. So it will not have this kind of structure. But if you try to freeze the water, so this is what I guess.
Because the reason I asked is, of course, we know things like critical opalescence also rely on large, almost macroscopic size fluctuations, not of velocity but of density, right?
Exactly.
So my question is, how is this large scale fluctuation different from that? I mean, that's what I'm trying to understand.
Yeah, so that, I guess, the kind of large scale fluctuation that you see there is of order parameter here. So displacement is not order parameter, it's just a dynamical feature, right? So in terms of the structure, the material looks exactly same. So if I give you a
no, that's a separate issue, right? If I'm at the critical point, let's not bring theoretical baggage into it. I'm just going to tag densities, velocity. I just make these measurements, and I'm wondering, is there something I can look at these pictures and say, this is dynamical heterogeneity, that is critical fluctuation? Is there some distinction like that?
Yeah, so I mean,
in terms of the statistics of these large voids or anything like that, or whether how the voids themselves move, is there any operational definition I could use based on the images I'm processing? That's kind of what I'm trying to get at. I don't know. That's why I'm asking.
Okay, yeah. So I know that there are some work where people looked at the scales of this and looked at the distribution, and what they compare to is with a critical point in terms of phase separation. So, but coming back to your question about liquid vapor transition, I don't think they will have this kind of dynamical heterogeneity, but I'm not entirely sure.
Okay, thanks.
Okay. Now, as I mentioned, so these are signatures that if you have a liquid, if you take an image of the liquid in terms of the displacement field, and if you see the signatures, you know that your liquid is going to undergo some kind of dynamical arrest or glass transition. So this is quite useful to detect glass transition sometimes. So we'll see why. Like, look at this example. So I told you already that tissue can be considered as an example of active glass, where you take a dense tissue, right? I mean, in principle, tissue can have all types of density. So this is a dense tissue. And then you look at the displacement of the cells in a dense tissue, and you see that the displacements are quite large in some regions, and they're also quite small in some region. And the gray pixels here, they show small displacement, and the white pixel, they show large displacement. And you see clearly dynamical heterogeneity. Just to compare, I have also kept one picture from the dynamical heterogeneity that you see in passive glass forming materials. And I'm not trying to say that the dynamical heterogeneity in a living glassy material is same as dynamical heterogeneity that you see in a passive glass, but I'm just trying to point towards a similarity in terms of dynamical heterogeneity. And this is not the only paper which claim to see glassy behavior in dense biological material. There are many other papers on cell migration on epithelial tissue or bacterial cytoplasm. They all claim to see some glass-like signature in these dense materials. There is also another paper which came recently on dense active colloids, where they see active glass material. So here are some snapshots from experiment just to give you an idea like how the systems look like. So this is assembly of E. coli. This is tissue. These are Janus colloids. So these colloids are painted with platinum, but asymmetrically, and then they breaks hydrogen peroxide in a fluid. And while doing this reaction, because it does it asymmetrically, it can get self-propelled. And I think someone asked me the question about gravity. So you can see here also gravity is being used because you have gravity, then the density also varies in the system. So you get a region in your system where the density is too high, and then it shows glass-like behavior in this region. And the final one, I'll talk about it later as well, but this is granular assembly, where because of the vibration, this 3D printed ellipsoids, they are self-propelled and they show some active glassy behavior. Now, to understand such active glassy systems, our approach would be to start looking at models. So if we have simple models where we start with the basic elements that give you some kind of active dynamics and also basic elements to make it a glass, then this is what we want to start with. And then we would like to see how different parameters that are representing activity, if we change them, how the system behaves, and can we have some generic understanding about those glassy active systems or not. So I started working on them, where I started to look at a 3D glass former known as Cobb-Anderson glass and included activity in some of the particles. And I also looked at an assembly of dumbbells, but for the interest of time, I will not discuss them today. And the model that I will be discussing in detail is this one. So this is a 2D glass former known as Cobb-Anderson glass, and this is essentially just the active version of it. So here is a schematic. What you will see here is an assembly of particles. These particles are soft because they have Lennard-Jones interaction, and then each particle is self-propelled along a direction which is dictated by this arrow which is attached with each particle. Now, to understand their dynamics, let's look at the equation of motion. So this is Langevin equation for each particle, and in the right hand side you see different forcing terms, different terms which are dictating the motion. So first one is a friction term, and the second one is the steric interaction or the Lennard-Jones interaction, such that the particles don't overlap with each other too much. The third one is the active forcing, and this one is, I mean, in principle, it can be of different sort. And as I mentioned in one of the beginning slides, I will be using active Brownian particle dynamics. So this is how I model the active forcing term. This is standard in the active matter community, where you drive each particle by a forcing which has a constant magnitude small f, and then along a direction which is ni. So ni has component cos theta and sin theta, and that means the orientation of the active forcing is theta, and theta undergoes a diffusion. Okay, so the mean of theta is so the theta dot is xi, and mean of that noise is 0, and it has a variance, and the inverse of this coefficient, which is the rotational diffusion, inverse of that is tau p. So we have two parameters to model this active force. One is f, which is the magnitude of the active force, and tau p, which controls the persistence time. We also, in principle, can have thermal noise, but to make our life simple, we'll throw away the thermal noise. When we looked at the effect of thermal noise, but for all the results that I'll be discussing today, I will not discuss the role of the thermal noise, but if you're interested, I can discuss them later. And then the density, number density of these particles that in this particular model is 1.2, and this is something that I've not chosen. It's standard Cobb-Anderson glass, so I just kept it there so that my system becomes a Cobb-Anderson glass in the limit when I put my activity to 0. Similarly, the number ratio of A and B, that's also fixed in Cobb-Anderson glass, which is 65-35. I mean, you can try other ratio as long as the material is glass former, I think it's fine. And then the mass and friction coefficients are taken to be 1.
So why is the active noise but 0 range correlation in time? Is there any particular physical way one can understand?
Actually, if you look at the noise carefully, so it's not it's not actually delta correlated in time when it's applied to the equation of purpose. So it's delta correlated in the evolution of theta. So then if you look at correlation of the forces, which is f cos theta and f sin theta, it becomes exponentially correlated noise. The time scale of that exponentially correlated noise is controlled by the.
Okay, so it's some kind of coarse graining you have done, which makes it uncorrelated on time scales. Bigger
Yeah,
than the coarse graining.
so there are few simplification involved. So first one is you see delta ij here. That means the forcing to two different particles are not correlated. But in terms of time correlation, what this is telling you that the particle is diffusing in terms of the orientation, right? So that means if this time scale is tau p small, then it diffuses very fast, and tau p is large, then it diffuses very slowly. And if it diffuses slowly, then theta remains more or less constant, and corresponding f cos theta remains constant. So it's being driven in a direction. So it can create long range correlation in terms of time by changing the tau. Does that answer your question?
Partly, but go ahead. I don't want to interrupt here because I mean, in principle, you could have, let's say, some power law for this psi correlation in time, but
Right, you can have, but I mean, what I want is I want to create some kind of correlation in the forcing here, right? So what I'm saying is that if I choose a delta correlation, delta correlated noise in terms of theta dot, that gives me exponentially correlated noise in terms of active forcing. So if
Can I ask something in the previous slide? Sorry.
Sure.
Yeah. So you mentioned some number ratio. So you effectively have two kind of species. But
Right.
as far as your equations are concerned, how are the two species any different?
I see. So they are different because the Fij term, this is the interaction, Lennard-Jones interaction term, and I have not explained it here, but I can tell you how they're different. So we have two species, A and B, and both of them are having Lennard-Jones interaction. So in principle, you have parameters sigma and epsilon in Lennard-Jones.
Yes.
And for a binary mixture, you have like three different sigma and three different epsilon, right? Because
Yes.
sigma A and sigma BB. Similarly for epsilon. And so these parameters are different. So we have three different type of sigma and three different epsilon such that it may mix certain binary mixture.
Since I'm not very aware, like are the AA type is interacting more rather than across particles? Is that the picture, or is
I mean,
it something?
Okay, so this also I mean the interaction energy scale is also, but if you forget about the scale, if you look at the diameter, then you will see that the A has bigger diameter and B has smaller diameter. So you can think of this as a mixture of A, where you have inserted some B particles,
okay,
35% of it, to make the original mixture eutectic. So it doesn't try to it doesn't try to go to a crystal easily. That's why you have added these defects of B particle, and people have tried with different ratio, and I think they came up with this ratio where it works very well, that it doesn't tend to crystallize and remains disordered for any typical.
Fair. One last question. Since you mentioned the energy scales of this Fij, how does that compare with the energy scale of your active noise, active driving?
Yeah, so that's a very interesting question. Actually, this is really important because you see, when you are looking at the dilute limit, right, then the energy scale Fij coming from the interaction is not almost there, right? So you can think of such a dilute limit where you can think of just isolated particles, right?
Yes.
So then that energy scale is not there. Then one simplification you can do to your equation is that you can say, okay, I have a force scale F and a persistence time tau P. So force by gamma is a velocity, and I multiply with persistence time, I get a length scale, and that length scale will control everything, right? Okay. But now, as you have correctly identified, that there is another length force scale which is coming from the Lennard-Jones, right? So that tells you that now I cannot make this simplification. I cannot say, okay, F into tau P is controlling everything, right? Because if that is the case, then I don't need to vary F and tau P. I can just have F or tau P. I can vary that, and then I can try to understand the behavior of the system. But because this another scale is there, I need to see what happens when we change F, and you will see that as you are changing. So Fij and the interaction term have the scale which is order 1. So you'll see when the active forcing scale will cross that length scale, something interesting will happen.
Okay, fine. Thank you. Please go ahead.
One question you say that the Lennard-Jones usually has a length scale and an overall scale for the potential, and you
Yes.
said the length scale is important because that's like the effect, some sort of related to the effective range of the interaction and so on.
Right.
Overall scale of the interaction does not matter for you.
Yeah. So the you mean the overall energy scale, right?
The energy scale.
Yeah. So this is what I was just trying to mention. So that the energy scale, or I mean, I can think of this as scale of stress or force. So this is important because when the energy scale coming from the driving, right? I mean, I like to think of them as a scale for forcing. So when the forcing crosses that energy scale coming from Lennard-Jones, there will be interesting things, right? So the system will show some behavior. So as I'm changing F, which is the magnitude of the active, and when it becomes similar to or smaller than or greater than this force scale coming from the Lennard-Jones, things will be different.
And then the length scale of the Lennard-Jones doesn't matter. There is usually a minimum of the Lennard-Jones at some scale, right?
Right. So it gives you just the like the shortcut of scale in your system that the particles are of this size, and yeah, so they don't play any other role than that.
Okay. And so the other question is the temperature that you are going to consider, the thermal noise, is very low, very large. Where are you in terms of the thermal noise?
So, I mean, the result that I'll be describing is completely athermal in the sense that there is no additional thermal noise. So, in a limit, you'll see that this term effectively behave as a thermal noise, because if your persistence time is small, then this forcing will be like a thermal noise, and you will have an effective temperature. But the additional term that you see here, that we have thrown away. So that means we are working strictly in the thermal limit. If you add thermal fluctuation to it, some of the physics that we'll see will also get away. But with a very small amount of fluctuation, we still see those phases surviving. But it's a complicated crossover that you see when you switch on the temperature, because some of the physics that I'm going to discuss now is dependent on the stability of the system, and which is most stable under in the absence of any thermal fluctuation. So just to summarize, the results that I'll be discussing in the next couple of slides, or in most of my presentation, is based on the results where the thermal fluctuation is strictly zero.
Yeah, go ahead. Sorry. Yeah, thank you.
Yeah. Okay. And then, as I mentioned, we have this two parameter F and tau P. Okay. So before I move on to the discussion on the phase diagram, let me also try to explain how should we approach the scanning of the phase diagram. So you see that when tau P is small, as I mentioned, that the persistence time is small, so the noise is like thermal noise. Right, so the behavior that you expect is like a thermal material, so it's not very surprising. But as you increase the tau P, the system is driven further away from equilibrium. So most interesting thing will happen at large tau P. Right. So our approach would be to reduce F from a large value to a small value, and you can imagine that F effectively behaves like strength of the noise, right? So at large F, you expect that the system will be as if it's at high temperature, and small f, it's as if at a low temperature. And then we want to see what happens at a fixed tau P when you reduce F, that is, you are kind of cooling the system, or you are reducing the degree of energy injection. And then you switch, change the tau P and go to a larger tau P limit and see what happens to the whole scenario that we see at a small tau P. Right, so this is our approach. So we'll start with the small tau P limit, and as I mentioned, that the trajectory of isolated particle looks like this at this limit when tau P is small. And what you see here is glassy behavior as we decrease F. Okay, let me explain how. So we can look at the movie of the system. You see the particles are jiggling. Also the force network in the system, they are also fluctuating. You can look at the potential energy or the kinetic energy, and they just show these fluctuations. And these are usual fluctuations that you expect in a typical liquid at a finite temperature. Now, as you decrease F, that is active forcing magnitude, you see that the kinetic energy goes down, right? And because you are driving the system lesser and lesser, so that's why the kinetic energy is going down. And as the kinetic energy is going down, you can also look at the density autocorrelation function that I showed you before, which measures how fast or slow the system can relax. And you see that a larger F, it relaxes faster. And as I'm decreasing F, the relaxation becomes slower and slower, right? Now you can again extract the timescales from there. You can plot it as a function of F. And then if you fit it using some divergent form, then you see that it diverges at a value of forcing, below which you can think of the material as a dynamically arrested, and above which you can again think of them as a liquid. Right? So this gives you this point, because I'm doing this whole analysis at a tau p, which is 1, let's say, and this gives you this red, right? So above which it's a liquid, and below which it's dynamically arrested. Now you can keep on doing this, and you get these red points over here for different tau p, and the dashed line here is from a prediction from the extension of random first order transition theory. This is a standard theory for glass forming material. So I mean, what we did there, I mean, it's kind of long to go into that, but the essential feature, maybe I can quickly tell you, is that when you have this kind of active driving, let me try to draw it here quickly. Sorry. Yeah. Is it working? Yes. Can you see my drawing?
We see your cursor, but not your drawing.
Now?
Now, yes.
Yeah, good. So what this analysis told us is that the effective temperature of this system is if you have thermal fluctuation T plus some constant into F square tau P divided by 1 plus some constant into tau P, right? And as we said, we have thrown away the thermal fluctuation, so you can ignore this. So this is the form of the effective temperature in the system. Now, if you are trying to understand how the boundary will behave, let's say that this is equal to the glass transition temperature or VFT temperature, whatever, right? So you see that already tells us that how F and tau P corresponding to this transition will behave, right? So it will decrease as 1 over square root of tau P for some time, and then at large tau P it will become constant. And this is exactly what you see here. Okay, but the main thing is, I mean, if you ignore that, the main thing is what you see at large persistence time limit is you see. Just give me a second. I just want to go to the full screen mode. I don't know why it's not working.
You try pressing play?
Yes, no, yes, thanks. No, I think my writing pad was connected, and that's why I had.
Please go ahead.
Yeah, so the main thing that we observe here is that large forcing, we see the system is behaving like a liquid, and as we decrease the forcing, it's undergoing some kind of dynamical arrest, right? So then we move on to the other limit, where tau p is infinite, right? So tau p is very, very large.
Can I ask you a question? Sorry. So you wrote the formula for the T effective.
Yeah.
So for how to define that effective temperature?
So the way we calculated it is that, let's say you have a, so this calculation was 1D, and it's like a very simple calculation. It's not something very rigorous. So what we had is just, let's say you have a single active particle in a harmonic well. By active I mean, let's say it's driven by thermal fluctuation, but addition to that, it has a forcing which has constant magnitude and some exponential correlation time. And then we measured, let's say, the x square average, the total fluctuation in the particle, and the mean square displacement, let's say. And then if you compare that with KBT, right, KBT effective, then you see that it shows you that T effective is T plus some function of F and tau P, and it turns out to be F squared tau P, 1 plus tau P of this form. Right?
If you take a single ABP and put it in equation, it's not going to follow the Gibbs kind of distribution, right? As the peaks are coming at the.
Sorry,
yeah. Sorry, if you put a single ABP in a confining potential,
It will not be like if we got beta U kind of distribution. The distribution is very peak near the wall. So
Right.
this,
I mean, yeah. So this will happen. Yeah, what you're saying is right, that if I take a active Brownian particle, put in a harmonic potential, then the distribution actually will become bimodal, but this is true at the limit when tau p is large. So there is a crossover. So at small tau p, you see a unimodal distribution and then it goes to a bimodal distribution. So I'm talking about the limit when tau p is, let's say, small, and that's why you have a relatively unimodal distribution. And there, if you look at the width of the distribution, it also measures how much fluctuation there is, and from there you can infer this, right? So you see that then that calculation is not correct for large tau p limit, right? But so here I've just drawn the line from the intuition that you get from small tau p. So the calculation is should be completely wrong in the limit when tau p is very large, but I just drawn the line to see what is the prediction that you get from small tau p.
but you know that for ABP, you can do this real expansion of pressure, and
Right.
you can try to find out that there is an effective ideal gas equation, and that gives an effective temperature definition.
I see.
Does it include this calculation that you have done?
Sorry, I lost you at the end. So you get effective temperature from the ideal gas expansion, and then
you can define, so for ABP, there is a thermodynamic pressure.
right,
Effective temperature.
right.
And that expression for the effective temperature, does it agree with the effective temperature you have shown here for the single particle case?
Yeah, I think it agrees, and it also has the same F square tau p kind of form.
Okay.
Yeah.
Okay. Thank you.
Okay, so let's look at now the other limit, which is infinite persistence time limit, where the forcing on each particle doesn't change over the simulation time scale, right? Because it's infinitely persistent. That means the noise on theta equation is 0, so theta doesn't change over the time scale. And in this scenario, what we'll see is that the physics of the system is dictated by the physics of jamming. So at large F, you will see this kind of flowing state where you see the particles are moving nicely, and also the force networks are getting remodeled easily. And you see the potential energy, kinetic energy are also fluctuating. But if your forcing is smaller than a threshold value Fc, you see that the force networks are static and the particles are not moving. The potential and kinetic energy are exactly like kinetic energy is exactly at 0, potential energy is exactly at a value where it gets jammed. So the system then have two typical states: either it's flowing or it's stuck, and that depends on how much forcing is there, right? So you can look at the kinetic energy. You see that the kinetic energy is fluctuating and finite. When F is large, as you reduce F, it's still fluctuating. But at F equal to 1.6 for this particular example, you see the kinetic energy is 0, right? So the system is stuck. So we can look at the average kinetic energy and plot it as a function of F, and then see where it goes to 0. And from there, we can see where the jamming and jamming transition is happening, right? We can also look at the distribution of forces, and you see that the distribution is if the system is if it is flowing, it's not force balanced. And if it is force balanced, then the forces on each particle is 0. That's why the distribution becomes like a delta function. So you can look at the width of the distribution, plot it as a function of F. And from there also, you can get the point where the forcing, at which forcing the system becomes stuck. Right? And that gives you this green square over here. So this tells you that the system will have a flowing state above this green point, and it is jammed below this point, right? And this point is kind of important because you can imagine if your tau p is not infinite but very large, then for a short period of time, the system doesn't know that the tau p is infinite or not, right? So whether the forcings are going to change over time or not. So then the physics of the system will be dominated by these green points over here when you are looking at this region. So let's move on to that part. So where so this is a limit where tau p is very large but not infinite. And again, as per our intuition, we expect that the system will behave like a fluid at very large F, and then it will behave like a dynamically arrested state at very small F, right? Now the question is what happens at intermediate forcing, and this is what happens at intermediate forcing, that the system is not completely flowing, it's not completely stuck. It's switching between two states, which is either flowing or stuck. And this is actually a very unique steady state that you see in this system, because there is no equilibrium counterpart of this, right? So in equilibrium, you never see a liquid which is flowing at this moment, and next moment it's frozen, again flowing the next moment, right? It's either a liquid or a solid. So you don't see something which is heterogeneous in time in terms of being fluid or being a solid. But here you see exactly that. So we look at this more carefully. So we look at the particles, and you see that sometimes move and then they get stuck. And the force network also gets stuck. You see the potential energy, initially it was fluctuating and got stuck. And then again, the force balance break, and then it starts moving. Right? So essentially what is happening here is that this, as we saw, that if your F is small and persistence time is large, then the system will get stuck because the forcings are not enough to rearrange the material, right? It's like a bunch of people who are stuck in a place. They are trying to move against each other, but they don't have enough force to move against each other. Now, if they have enough force, they definitely can move and fluidize, but if the forcing is small, they will not. But this kind of force balance situation also depends on in which angle the theta is pointing at for each particle. Here, the tau b is large, but not infinite. So in principle, the force balance will eventually break and the system will start flowing and get another such force balance structure. Right? So what the system is doing here is they self-organize towards these force organized structures. And once they are in those kind of stable state, they remain there for some time because the force balance breaks after a certain time and the system stays there. So there is a second phase. And again, it starts to remodel and it starts flowing to find out the next such structure. So when we saw this for the first time in like few years later, it was merely an observation from simulation, but very recently, there is an experiment which happened in Bangalore, where they did the experiment, this kind of granular ellipsoid. And what they see is they, in the dense limit, when the ellipsoids are very persistent, they see this kind of intermittent jamming and jamming event. And also you see similar type of time series that they see in terms of displacement, which is very similar to what we see. So this is quite exciting, but there is also a few things to be done in future that I will try to point out later. Now we look at the displacement patterns that it creates during this. So we looked at the velocity patterns the system creates.
Sorry. Of this intermittency. I mean, visually, I can see what you want to say, but is there a way of mathematically characterizing this? Something that you can compute, because show when there is intermittency and when there is not.
Yeah, we did that. So can I just like wait for few minutes? I can actually show a slide where I can show you how exactly I characterized it. So, or maybe I can do it now and then I can.
No, don't change. Go ahead. We can talk about
it's in like few slides later, so I can quickly show you that. Okay, so to define this intermittency, what we looked at is we just looked at the kinetic energy time series, right? Because we saw the intermittency in the time series of kinetic energy. So we calculated the kurtosis, and typically, if it is a Gaussian time series, then the kurtosis is just flat and it's 3. And that you can see for a forcing, which is, I'm not sure whether you will be able to see these numbers, but just believe me, this is like large F. And then you see that the kurtosis is all times. But when the system starts becoming more intermittent, then at very large time separation, this is still a Gaussian-like fluctuation. I mean, so what we are looking at is the separation in the kinetic energy for different time. And so this variable is still like Gaussian, so the kurtosis is still 3. But as we are coming to smaller differences because of the spike-like nature, you see that the kurtosis has a tendency of divergence at small time limit. And this is typical in like fluid turbulence, where also people characterize this by this quantity kurtosis. And then I also subtracted 3 from this because this is the standard value that you get for the Gaussian fluctuation. So this is the excess kurtosis. And now if I plot the excess kurtosis as a function of f, you see that it, I mean, there is no sharp transition to say, right? But it clearly increases rapidly, and that tells you in which region it's very intermittent and which region it's not, right? So finally, the phase diagram, when you look at the phase diagram, you see that I have used a color, and the color is coming from the log of this excess kurtosis. Right? Okay. Now, sorry, I'm just having some trouble in hearing you. Does that answer your question?
Yeah.
Okay. Yeah. So then we look at the, as I mentioned, we looked at the velocity patterns, and we looked at the energy spectrum, and it shows the signature of turbulence. So in 2D turbulence, we see this Kolmogorov exponent -5/3 in the inverse cascade regime, and you see the same thing happening here. And as you now decrease F, the forcing, you see that the time scale over the system was flowing gets shortened. Most of the time it remains in a jam state, and it flows for a short time and then again get jammed. And if you reduce F to a smaller value, you see that the region, the time scale over which it was flowing gets shortened so much that the period of flow becomes almost like isolated events, right? So we wanted to understand what the system is doing during these sharp events. And what they do is essentially like SLB events that use sheared amorphous material. If you take a glassy or amorphous material, if you shear it very slowly, this is known as athermal quasi-static shear. You see that the stress strain plot looks like, right? And now the stress increases as you strain the system, but there are these drops. So the stress builds up, and then there are plastic rearrangements happening during these drops, and they look like this. And if you look closely to these plastic rearrangements, you see that they actually have some interesting structure. So if you go to the core and look at the displacement and project it out along the radial and the azimuthal direction, you see that they have this quadrupolar structure. And these are actually dictated by the kind of constraint you have. You are doing a deformation on the system by preserving the volume. So these are the excitations allowed, these are known as SLB excitation in a typical elastic medium that you can see. And this is exactly what we see in our system in this limit, where you see these isolated events. You see the signature of them in kinetic energy or in potential energy or local stress. And if you look at the displacement during such an event, and again, if you go to the core of the displacement and then take the projection along the radial and the azimuthal direction, you see in the radial direction, they have this particular structure. Also, the displacement decays as 1 over r. This is also another prediction from HLB. So that means the excitations that we see here in this small f limit are of HLB type. The only difference from the sheared case is that when you apply some global shear, there is a geometry that you are setting. So all the HLBs are oriented because they have to respect that symmetry. But here, I'm not applying any global shear. The particles are getting these plastic rearrangements through local rotation and local plastic rearrangements, and it doesn't have any global structure. That's why the orientation of the HLB can be anything. Like it can be anything which is not true for the simple athermal quasi-static shear. Okay. Now, just to summarize this part 1, we have built up this simple model active glassy material, and we see that at very small persistence time limit, we see an interesting slowing down effect as you decrease F and system undergoes a glass transition. In the infinite persistence time limit, the system's behavior is affected by the physics of jamming, and in the intermediate but large persistence time limit, we see intermittency and this signature of turbulence and HLB events and many very interesting things. Okay, so are there questions until now?
Yeah. I want to so you find this contour of energy cascade scaling, right? But in turbulence, usually the energy is injected from a macroscopic scale going down to the microscopic.
Right.
The opposite happens, right? You are injecting energy through the driving at a very microscopic scale, that flowing out up in a larger scale.
Right.
Understanding in a similar hand-living argument as in the contour of
Yeah, so actually this is not unique to active system. So this is the regime of inverse cascade. So if you look at a 3D liquid, exactly what you said happens, that if you drive the system at larger scales, then you create the eddies, which breaks into smaller eddies, and the energy is getting dissipated at the scale of small particles, and like the particles of the fluid. But if you take a 2D liquid, then it can be shown. I'm not very familiar with the whole calculation, but it can be shown that the reverse happens. So it's a regime of inverse cascade where you drive the 2D liquid at small scales, then it creates larger and larger eddy. Right. So essentially the same thing is happening here, but normally when they do it in the fluid turbulence, they periodically drive it at some point or use some noisy driving. We have some different form of driving. But apart from that, this is the scenario that you also see in 2D turbulence, where you have this inverse effect that you inject energy at smaller scale and then it creates eddy of larger scales.
It is at this stage, it's mostly just an observation that you get the same scale.
Right. So we don't have any understanding that why the exponent. Because this is not a usual Navier-Stokes liquid, so I don't know why it should be exactly minus 5/3. But for different system, people have seen that this is minus 5/3. Also, we don't have any understanding why this minus slope is there. But I mean, we just did this analysis to see whether this has like signatures of standard turbulence, like whether the energy spectrum has this power law behavior or not, and we saw that the exponents are similar, but we don't have any theoretical understanding why the exponent should be such. Okay, so are there questions on this part? Then I'll move on to the next one.
In this one more thing that you have, the density is not coming into the phase diagram way, right? You're not varying the density.
Right. So at this moment, I'm just keeping the density fixed exactly to a value what people use to model this Cobb-Anderson glasses, just to, let's say, compare with the results. In principle, you can also vary the density. So then there will be interesting things that will happen. So, for example, the physics of MIPS will come into picture. Right? Because here the density is so high that you cannot create the density gradient by driving it by activity. But when you reduce the density, it will show MIPS at low density. It might also form jammed gases, and there will be also definitely phases like active gas, etc. But it will really become a very complex phase diagram. So for now, I'm just trying to like for the next part also, I'll try to confine myself in this limit. But definitely, it's very interesting to extend this for lower density. I mean, for higher density, I don't think there is anything very surprising to happen, because more or less it's already pretty dense, right? But if you reduce the density, then there will be interesting things that definitely will happen, because there are many works where people already look at similar models, but at relatively lower density limit, and they see motility induced phase separation and other stuff. Yeah. Okay. So the next part is to when we try to understand the rheological behavior of such a material. So here you can see the cartoon. So what I want to do is that I want to take an active material and put it in a rheometer and try to shear it, and I want to see what happens, right? And this is a standard framework that I will be using for the simulation. So I will be confining the material between two plates, where the lower wall is fixed and the upper wall is moving with a constant velocity. And the velocity of the upper wall is determining what is the shear rate of the system. And here is the equation of motion for each particle. This is exactly same that we had before, except this new term, because I'm also assuming that there is a solvent fluid which is also moving affinely, and it has this simple affine form, and the particles in my glassy material is being dissipated to that fluid. So this is the only additional term that we have, and apart from that, everything else is same. There is also another difference. Earlier, I was looking at system under periodic boundary condition. Now I have a system where I have periodic boundary condition in one direction, but in the other two direction it's fixed. And the boundary has some interesting effect. And in fact, the main kind of behavior that we are going to see is also dictated by the boundary. And the equation of motion for the particles in the boundary are quite simple. The particles which are part of the lower boundary, they are not moving, they're completely static. The particle in the upper part of the boundary, they are moving with a constant velocity. So this is equation of motion for all the particles which are in the bulk, not part of the boundary. Now, we also had two different parameters before, F and tau. We now focus our attention to a limit when tau p is large but not infinity. Let's say we fix tau p to 10^3. Then we change F to go from dynamically arrested state to intermittent state to liquid state, whatever. So F is one parameter, and then the other parameter that we have is the shear rate, which is gamma dot. Right? So this dictates how fast or slow we are shearing the system. So essentially, what we want to understand is how the system behaves when you drive it both locally and globally. So F will control the driving at the scale of particle, and gamma dot will control the like how much it's being sheared at the global scale. So we constructed a state diagram. So
Remind you, we are around 5:20. So would it be okay if you can wrap up in 10 minutes?
yeah, sure. Sure. I'll be faster. So there are some slides which I'll skip fast.
Yeah. I just wanted to give you a sense of it.
Yeah. Okay. So the state diagram in the F gamma dot plane looks like this, which has multiple type of states. I will not go into them, but the state that I am interested in is called the shear induced order state. Okay, and before I start discussing the state, this is important to notice that shear, in some sense, at least very naive the way of energy injection, right? So you might think that, okay, if I shear the system, I'm going to destroy the order. Though there are many cases where you see in different soft matter system, if you shear the system, it might help you to get ordered, like or aligned, or shear can form crystallization, etc. But here, my first naive assumption was that I will not see any ordering, at least in terms of shear, but this is exactly what you see. So here the particles are actually colored according to their orientation. So what you see in the color bar is this is a color bar from -1 to +1, and what I plotted is the angle of each particle. By angle, I mean the angle of active forcing divided by pi. So +1 means it's plus pi, -1 is minus pi. And you see the particles in the upper half, they are more reddish, which is like having angle pi/2. That means they are more oriented towards up. And the particles in the lower half, they are more oriented towards down because the angle is around -pi/2. Right? So you see that as I'm driving the system is getting segregated in regions where they have a preference either towards pointing up or towards pointing down. And the particles in the middle, they are more towards right or towards left. So we look at this state more carefully. We see that the velocity profile in this state is linear, which is reasonable considering you have a finely flowing material. And then the stress also increases initially because of some elastic response, and then there is yielding, and then goes to a steady state. But the most interesting thing is it has a finite order parameter. So there is an order parameter that grows and saturates. So I'll describe the order parameter now. So what we do here is we calculate the average of sin theta across the system. And why you do that? Because as I told you that the orientation is here towards up. So the sin theta average is close to 1. And here towards down, so it's close to -1. So I get a profile like this, which is a profile of phi of y. And then I take a first Fourier mode of this to get the order, which is psi, right? So if you don't want to go into the detail of this order parameter, just notice that the order will be only there if p theta y has some structure, right? So if p theta y is uniform in theta, then the average of sin theta will give you 0. So the order is coming because p theta y has some structure. So we thought we'll try to write down the theory for p theta y in terms of Fokker-Planck equation. So here is the equation where the first term is dictating the evolution, the second is the drift along y. And this is being done with active forcing, right? So it is being driven by f sin theta with the prefactor of mu, which is the effective mobility. And then the third term is the diffusion along y. So here y is the shear gradient direction. And final term is coming from the diffusion in the theta sector, right? And so if you look at these parameters, we know what is f tau p, but these are two new effective parameters, d and mu. And for now, we don't have any idea what is value of d and mu. So we look at the equation, which is like this, and then at steady state, we can throw the first term, so it becomes just this. And then we do a Fourier decomposition of p theta comma y in terms of its Fourier modes. And again, to make the calculation simpler, we truncate the series using the Galerkin truncation method of keeping just 3 terms. And if you do that, then you can also apply the boundary condition. And as we have these fixed walls over here, that means the physical current at these points are 0. So you can impose that boundary condition, and that gives you the closed form solution for p theta of y. Obviously truncated up to some form, but this is the form, right? And you notice that there are parameters alpha and zeta, etc. But these are also derived from the microscopic parameters we have before. And some of them are known parameter like system size, active forcing, tau p, etc. But then there are some parameters which we don't know, right? Which mu and d. So what we decided next is to measure mu and d from our simulation. So we can go back to the simulation and look at the velocity along y and plot as a function of sine theta. And we see that it is completely linear, obviously within this error bar. And then from the slope, you can estimate what is the effective mobility. We can also look at the mean square displacement along y, and then we can plot it as a function of t and fit it to get the diffusion constant. Now, once you get mu and you can put them into the expression that you have, because now there is no free parameter left. And this is the prediction for p theta of y analytically, and this is what you get from simulation, right? And you see that they match quite well, not in terms of qualitative structure, but also if you compare the numbers, they match quite well. So to summarize this part, I would say that in the presence of this kind of very high shear rate, you see this shear induced ordering in this system, which is the ordering of the orientational degree of freedom. And note that the orientational degree of freedom is not directly coupled to shear, right? So the dynamics of theta is independent, but because of the shear, they acquire enough diffusion to arrive where they want to, and that's why they get segregated. And also the single particle focal bank description works quite well, right? So, sorry, yeah. Any questions up to that? Then I'll go to my summary part. Okay, so if not, I'll go to the summary part. So the whole study that I did, I think it adds some new direction to the field of both active matter and glassy systems. But I mean, I believe not just a trivial addition to the, but it gives rise to also interesting physics like intermittency and shear induced ordering, which are kind of new phenomena that you were seeing, which is coming as emerging feature in this. Also, there are interesting experimental direction. We recently looked at how aging happens in this kind of dense active material. Aging is a unique feature that you see glassy material that close to the glass transition. The systems doesn't go to equilibrium state, rather keeps on changing its behavior over long. So what we wanted to ask in this work is that whether you see similar aging behavior that you see passive glasses or not. And we saw that there are some different interesting type of aging that you can see in this active glasses. So it's an interesting question in terms of experiments that whether you see similar aging behavior in experiments. Like if you do an experiment with active colloids, whether you are going to see similar aging or there are features that are coming. Also, currently we're trying to look at the rheological response of such material by measuring G prime and G double prime omega, which are frequency dependent, elastic, and loss moduluses, and trying to extend the soft glassy rheology theory for this. But again, experimentally, it's an important question that if you take tissue or such dense active material, what kind of frequency dependent response you get in terms of elastic and loss modulus. There is also another new interesting direction. So I got recently interested in non-reciprocal systems. So typically we know that of the interaction in terms of fundamental forces, they are reciprocal. But if you are talking about the effective interaction of two particles, which is embedded in a medium, then if you drive the medium or the particles far away from equilibrium, then the interaction between them can become non-reciprocal, right? So we looked at an example recently where we have some active particle moving through an athermal solid-like material, and you can see that they create this kind of density waves around them while moving, and therefore the effective interaction between them becomes non-reciprocal, right? So it doesn't remain reciprocal in nature. We're also trying to look at the collective behavior of some such non-reciprocal mixtures. So if you take a bunch of non-reciprocal particles, put it in a confinement, how they behave collectively. But the main interesting thing that I want to look at in future is that such reciprocal behavior, how this affects the slow relaxation of this non-equilibrium solids, right? Such classes. And finally, I would like to say that I believe that this whole study on dense active matter adds a step towards understanding living matter, which is a very complex in nature, but at least this kind of simple model-based approach will give us some understanding and intuition. Okay, so I'd like to acknowledge all my mentors and collaborators, and thank you for your kind attention.
Thanks, Rituparno.
Thank you.
Are there any more questions? You asked a lot of questions.
Yeah, I just wanted to ask one small question. On the computational side, how intensive are these kinds of studies compared to, I don't know what, but you tell us.
Okay, so like typically, if you are asking me, let's say the time scale it requires is like few hours to few days, because we don't go to like a very big system size. Typically, this system has good convergence in terms of system size. So, but there are obviously some examples where they don't converge very well in terms of system size. Then it might be very long. But I would not say it's computationally very challenging in terms of the time it takes. But what is quite interesting and also difficult sometimes is to identify key features that will need to be incorporated in these systems, and sometimes they can be computationally very difficult. For example, if you think of a material where, let's say, the particles are coupled with the fluid, then you also need to do a multi-scale where you are evolving the fluid with a much finer date. And I think some people also pointed out, let's say the particles are moving towards the gradient of a fluid, and then they have complex interaction between them because they're competing for some resources, etc. So if you include all stuff, then it can become very computationally challenging. But the kind of thing that we are doing now is, I would say it's not at this moment very computationally. It's typical and of the same order of time scale that you need to understand simple classical glass forming materials.
Okay, thank you. That's the last question I had. Thanks for a nice talk.
Any more questions? So I had one question. So in the first example, you've taken the underdamped Nanchua description of ABP. If you go to the overdamped limit, which is the typical modeling of ABP, do you expect some of these results to change?
Yeah, so okay, maybe I can very quickly go to my equation. So the idea is, maybe I can just show this one. So you see that this is underdamped equation, right? And then you can estimate the time scale of vibration or time scale of inertia. And because my M and gamma are 1, then this is 1. And then you can also measure the time scale which is coming from friction, and that is also of the order 1. So in that sense, it's not truly in the inertial regime. So though we have a term here, it's not actually in the regime where you see the initial effects. For that, you need to change. But very recently, there are some groups who looked at inertial effects in active Brownian particle, and then they show that inertia actually have very strong effects in terms of the stability of MEEPs, etc. But for all the results that I showed you, here, though we have the inertial term here, it effectively doesn't matter because the choice of M and gamma we made.
And in the last example that you showed about the non-reciprocal kind of interactions, there were these works recently about by these groups in Chicago about chiral phases with the non-reciprocal interactions.
Right.
Expect that those phases would affect any kind of classic behaviors in your systems when you introduce the non-reciprocal interactions?
Yeah, so typically they looked at few systems as far as I know. One is like the phase separating mixture, and other one is the Vichek-Lykov model. And they, I mean, at least the original model doesn't have much tendency to form a glass. So that is why I'm currently working with Vincenzo on developing a model for these non-reciprocal glasses. So what we are doing now is that we are considering a standard passive glass former, but considering interaction between two particles, which is non-reciprocal. Let's say the Vij is not same as Vi, right? So we have a parameter delta, which is controlling how non-reciprocal they are. And then what we are trying to do next is we are trying to understand that as you increase the delta, how the nature of the glass transition changes, right? So in some sense, when you have this delta, you mean that the particle A is affecting B different way than B is affecting A, right? So they never finds a steady state because the energy minimization doesn't work there. So it's kind of a dynamical frustration you are introducing. So it's possible that by doing this, you can make a system more glassy because in some sense you are introducing more frustration.
Original work, there was no disorder, right? There was in the original work of
in the yeah, so in the like the model they looked at, for example, for Vichek model, etc., there is no disorder. So there is no glassy behavior in those systems, so to say, right?
Okay, thanks, Rituparno. Yeah. If there are no more questions, let's thank Rituparno.
Thank you.